Today I'll be taking two sessions. We'll start off with a quick introductory session on Nvidia Nemo, which is a toolkit from Nvidia for doing building conversational applications that includes technologies such as ASR, TTS, and NLP. We are going to be using Nemo tomorrow in a hands-on session to train our own large language model on the Hindi language. So this is supposed to give you a bit of background on what Nemo is and how it works. After this short introductory session to Nemo, we'll have an extended session on uh, a research survey on large language models, where we'll walk through what are the advancements that happened over the last 2 or 3 years that led to the rise of these large language models. So with that, let's start with our first session. So we'll be discussing about NVIDIA Nemo. So NVIDIA Nemo stands for neural modules, and it's a toolkit from NVIDIA for building your SOTA convolutional AI models. So this is built on top of PyTorch and PyTorch Lightning, and this is an open source library which consists of technologies which allow you to build for mainly three main use cases or three main technologies. That is your ASR, LP, and TTS. Uh, All the latest models or research that is being done by NVIDIA, those models are being ported into Nemo, as well as the pre-trained models are available in this particular library. Right now, it has support for multiple different languages, for instance, 8 for ASR and 5 for NLU. And these pre-trained models give performance as good as any model in your cloud service right now. As I mentioned, NVIDIA Nemo is an open source toolkit, so it's freely available on GitHub, and we can clone them and start building on top of it. Nemo is again integrated with PyTorch and PyTorch Lightning. So if, developers who are familiar with PyTorch can also start customizing the code that is provided inside of your Nemo. It does have easy to use APIs. This is something that we'll see in our demo tomorrow on how easy it is for us to uh, pre-process data for deep learning, as well as start the deep learning process and uh, manage the end-to-end workflow of going from data all the way to a well-trained model. Nemo is highly optimized for training on NVIDIA GPUs. So it completely uses NVIDIA's CUDA stack, and this can easily scale to thousands of NVIDIA GPUs. And as I mentioned, a lot of the pre-trained GPU checkpoints are available online in NVIDIA NGC as well as Hugging Face. To give some context on what are the models that are available right now. So for ASR, you have models such as speech-to-text, speech classification, speaker recognition models. And again, these achieve almost state-of-the-art performance on the standard benchmarks. You also have really high-grade models for NLP in tasks such as question answering or translation, and also with your TTS tasks, where you have the latest models available right now. So the core of Nemo is something that is known as the Nemo Collections, and this is basically an end-to-end code for building and training a model for a particular task. So if you want to, let's say, build a model for translation, um, the steps for doing this is just importing a translation model from the Nemo collection, setting the path to, let's say, the training or the validation data, and then doing a model.fit. So within these three steps, we're able to train the model. Again, Nemo is built on something that we call neural modules that we'll talk about in the next slide, which makes the debugging of deep learning applications much faster. And using Nemo, we can train and fine tune models for a particular domain. And it's one of the key use cases of Nemo. Uh, Again, this we'll talk about in a while. And it's tightly integrated with PyTorch and Lightning modules. So again, if a developer is familiar with PyTorch, they can easily modify the code that's present inside the Nemo collections. So one of the key points of Nemo is the neural types. And neural types are essentially deep learning tensors, which have two properties. One is the type of the tensor. So a type could be a mill spectrogram type, or let's say a spectrogram type, something like that. And the second is the dimensions of the tensor. So this doesn't just include the shape of the tensor, but also what each and every axis in the tensor mean. So in this particular example, let's say we have a output tensor with three particular dimensions: batch, the, d dimension, which could be any embedding size, and then we have the time dimension. Uh, and secondly, associated with that is the type of the tensor. So in this case, it's a mill spectrogram type. Now, why this is important is because in Nemo, we can specify at each level or each function what is the input type that we're expecting. So if in case we get a input tensor, which happens to be three-dimensional in shape, but the shape differs. So instead of having the batch dimension first, it has the time dimension, and it's of the size t, uh, comma b, t comma d comma b. That's going to throw a mismatch, and we can debug it out. Similarly, if you're expecting, let's say, a MEL spectrogram type, and instead we get an MFCC spectrogram type, again, this is going to throw a mismatch error. So these neural types or these neural tensors are one of the key design concepts of Nemo, and they greatly minimize any runtime and compile time exceptions that we get with deep learning. Second, Nemo supports mixed position and distributed training. So NVIDIA A1 GPUs have specific tensor cores to support FP16 computation, and they have twice as many uh, computation components for FP16 compared to, let's say, FP32. So in recent deep learning era, it's more common for people to start training the models on a lower precision or mixed precision setting, and Nemo completely supports that, and it can be easily scaled into a multi GPU or a multi-node setting. And again, Nemo is built using Hydra framework. So all the configuration that we have with the model, we don't need to specify all of it. A lot of the configuration is built in. We just use this Hydra framework to specify some configuration, such as the training dataset or the validation dataset, something like that. One of the key workflows in Nemo is its ability to be connected with Riva. So Riva is a toolkit from Nemo for a toolkit from NVIDIA for deploying your speech and NLP models. And the use case of Nemo is that you could take any existing pre-trained model and then customize it for your particular domain. So if you um, have domains such as, let's say, biomedical use case, we can take any English pre-trained model, use a Nemo collection to fine-tune it for a biomedical use case, and then use the tool called Nemo to Riva export tool to convert your Nemo models into the Riva format. So this allows for a very rapid experimentation where we quickly execute a workflow such as training or fine tuning, and then instantly deploy it using Riva. And lastly, Nemo has extensive support for uh, data preparation exploration. So for doing any sort of text or speech processing, there are already inbuilt scripts which are optimized to uh, run efficiently. So that was a very brief introduction to Nemo. And again, in the tomorrow's session, we'll have a deep dive into Nemo's code, and we'll also be pre-training a GPT model using Nemo. Um, If you have any questions on Nemo so far, feel free to put it in the chat. So I'll briefly be starting with our next session, which is on large language model pre-training. So I'll just share my screen and get started with that. Meghna, is my screen visible?
Yes, Raman.
Thank you.
Visible. Yeah.
Okay, so what we'll have do now is have an extensive session on large language models, and specifically we are going to review all the recent research that has happened in the last few years, which led from going from a small model such as GPT to the current large language model such as, let's say, ChatGPT. And the idea here is to look at each and every component, starting from the data part of things all the way to the architecture and the training techniques that have enabled this transformation to go from a small scale language model to a very large scale language model. So again, feel free to uh, post all the questions that you have in the chat. I'll be frequently stopping to look at the questions that we have, if any. So
Hi,
the
Raman. Sorry to cut you. I think there is this one question.
yes,
Just a
check that.
second. Yeah. Let me just ping you that in that case. 1 second.
Okay, so we have a question. Explain the BDT parameters once more. Sure. I'll just go back to the previous slide. I also have another question. Any scientific applications? So I'll share my screen and I'll explain about this. Some details on the Hydra framework. Okay. All right. So let's start with the first question. That is the B, D, and T tensor. So any input that comes in NLP or speech. So let's take an example of NLP. And if we have, let's say, a sequence of 10 words, and we have just one batch size, um, and this is the only item in the batch. And let's just say that um, our embeddings are of the size of 512. The input that we'll be passing along would be of the size 1 cross 10 cross 512. So that would mean that the batch size is 1. The time dimension, in this case, we are taking time dimension in the middle. Time would be 10 because you have 10 time strips or 10 tokens. And lastly, the D dimension or the embedding dimension would be 512. Now, this is not the only way to be representing these numbers or these tensors. One could also uh, uh, change this up and have a format of BDT where your batch dimensions comes first, then you have 512, and then in the end you have um, the time steps, which could be 10. Now, uh, imagine if we did not have these neural types, what would happen is that the input that's being passed into a particular function in a deep learning code would have uh, three tensors, sorry, tensor of rank 3, and then you'll be doing a lot of operations on those tensors. And if something goes wrong, you wouldn't be able to catch because the operations that are happening are happening on a between two tensors of rank 3, and that's a valid operation, and things are working fine, code is executing, but outputs that are coming are not correct, the loss is not decreasing and something like that. But if you had a property for each tensor that clearly tells you which rank is your batch dimension, which rank is your time dimension, and which rank is your embedding dimension, it makes it very clear, because you can define that these two operations are supposed to happen between a tensor of BDT and again with a tensor of BDT. And if uh, one of your dimensions have by mistake altered, let's say you did some transpose and all of a sudden by mistake it's B, T, and D. At that particular line, it is going to throw an error because Nemo was not expecting BTD, rather it was expecting a BDT. Um, so that was uh, so that's how this property of uh, the B, D, and T come into picture. At the same time, you can also specify a type or the type of the tensor. So you can specify that the input that you're expecting is going to be, let's say, a spectrogram type. And if the input is a mill spectrogram type, it's acceptable because uh, melt spectrogram type is a very specific type of spectrogram. So it's acceptable, the code executes. However, let's say you want to be strict. You want to make sure that the input at that point is definitely a melt spectrogram and not any other type of spectrogram. Well, you can specify that what you're expecting is melt spectrogram. As soon as the input comes in, Nemo is going to check what is the type of the tensor. If the type happens to be spectrogram type, well, that is ambiguous because we don't know what exactly is the spectrogram, so it throws an error. If it happens to be an MFCC spectrogram, again, that is directly wrong because it's not the spectrogram that we're expecting. So this is how um, the types in your neural tensors work. I think the second question was, are there any scientific applications? So I'm not sure what you meant by the question, but if you meant the what are the different tasks that we can do, these are a non-exhaustive list of tasks. So these are the most common tasks in each of the domain. So for ASR, we have tasks like this is automatic speech recognition, speech to text. You have speech classification, that is classifying speech into a particular class, or things like speaker recognition. And we can build some application on top of it. So if you wanted to build, let's say, um, a meeting summarization, right? We would be using speech to text to be transcribing all the meetings and using speaker recognition to recognize who's the person uh, who's speaking right now, and then have some transcripts generated to kind of build a meeting application. Uh, so maybe if you could clarify that part on scientific applications, I could probably answer it better. So the third question was, what is the Hydra framework? So typically what used to happen in Python programming is that all the configuration was provided either through your command line arguments, or you had a very messy YAML file, and there was no standardized way to change the configuration. So if you were using just command line arguments and you had 10 different arguments to be passed, things like batch size, number of epochs, number of training parameters, so on, and number of uh, file paths, etc., it becomes very messy to handle it. Now, if you decide to, let's say, transfer all of these arguments into a YAML file, it becomes even more difficult to manage it because for each different experiment, you would have a YAML 1, YAML 2, or YAML 3, etc. To kind of organize this process, Facebook came up with a tool called Hydra framework, and it makes it much easier to use configurations. So one of the advantages is that you don't have to write a code to read from YAML file. Rather, you just um, add a Python decorator onto a function. You just call hydra.main. You'll automatically get the configuration uh, completely read and formatted into a Python dictionary. Apart from that, it's very easy to manipulate this. So if you're using Hydra in your code and you want to, let's say, change the train path, you just do something like python 3 main.py. Then in the configuration, you just put a space and say train.ds dot manifest file path is equal to something. So it's much easier that way. And one of the other advantages is you have something known as hierarchical configurations. So let's say your training dataset could be ImageNet or Cifar, or let's say some Flickr, right? You can make a hierarchy of configurations wherein you have a main.config or main.yaml file. In that same folder, you got a subdirectory called validation dataset. Each of the validation dataset could have three more configuration files: imagenet.yaml, cifar.yaml. Hydra will automatically understand that you're trying to make multiple different sections for this particular configuration, and it'll automatically load it and run experiments on all the datasets. So Hydra itself has a lot of interesting functionalities, but in Nemo it's mainly used so that it's very easy to use this configuration. So if I'm, let's say, training a coordinate model, a lot of these things I don't need to change. I just need to keep it fixed. Rather, while running my um, Python 3 Nemo slash train.py, I would only do something like train.ds manifest file path is equal to my file.json, something like that. So these were the questions I had. Let's see if there are any more questions. Sorry, I need to stop sharing the screen so I can look at the questions. Why time step 10? That was just an example that I took. So let's say you wanted to have a longer sequence length of, let's say, 128. You could always have that particular number as your time step. So you could have a sequence of 128, and if sequence are shorter, you can just pair it up. So that was just an example. Uh, and what is time step with respect to ASR? So with respect to ASR, a time step would refer to a particular second. So let's say you have a sample data of 16,000. In each step, you would have 16,000 samples, and each of those samples would be, you can consider to be one time step. And again, typically what happens is 16,000 is way too much. It will be eventually be processed to a much more manageable size. So again, time step would vary as you keep processing data further and further. And thanks for all the questions. Please keep posting questions. It'll be very interactive. So I can share my screen. I'll go to the LM survey part. Okay. So the story for our large language models starts in 2017 with the introduction of the transform architecture. And transform architecture for the first time enabled us to do large scale pre-training and then fine tuning for a particular task. This kind of a paradigm was previously only available when your computer vision, where you had models like ResNet, which was trained on, let's say, all of ImageNet, and people then fine tuned it for a much smaller task. And with the transform architecture, people started developing variants based out of it, such as the BERT architecture, which only consists of the encoder part, and the GPT, which only consists of the decoder part. And over the course of this series or this session, what we'll do is we just focus on the decoder side of things. and we'll take a look at all of the components, which starts from the data, the model architecture, the pre-training tasks, um, any tuning, adaptation, etc. That all of the things that happened, which led from GPT-1 all the way to GPT-4. And we'll also talk about each of the individual components in this architecture. So yeah, let's get started with that. So the existing paradigm we had in NLP after the introduction of transformer was that we had a pre-trained transformer which was pre-trained on a large general English corpus, and then it was adapted to a particular domain. Now either it could be using domain pre-training, such as let's say taking the BERT model and then doing domain pre-training on a lot of biomedical data, which would give you something like a BioBERT. Or you could take your BERT model and then fine tune it for a particular task, let's say question answering. And this approach worked really well because compared to uh, previous approaches, you had to use only a small amount of fine tuning corpora. And most of the learnings actually came from this really large general corpus that the model was initially pre trained on. And one obvious way that people realized to improve this paradigm is to keep increasing the scale of the model. And what happened as a result of this is that we went from a small model, such as GPT, to models having size larger than 10 billion parameters. And most recently, in this last 1 year, we have had models uh, which are exceeding the size of 100 billion parameters, and these are something that we now call as large language models. And the trend in LM research has significantly exploded after ChatGPT was introduced. So this graph shows that uh, language models have been constantly being researched upon over the last 4 years, whereas large language models in particular have seen a certain spike since November last year. And the idea with this session is that we'll kind of have an overview. We'll talk about what has changed between a pre-trained language model versus a large language model, and then we also go deeper into what are these changes. So we'll start by highlighting the key differences between a pre-trained language model and a large language model. So we all know that large language models typically have a much larger size as compared to, let's say, a smaller model like a BERT or a GPT-1 or GPT-2. But there exists no such criteria that the model has to be greater than a particular limit to be called a large language model. Rather, um, LLM can be defined based on these three main three main kind of ideas. One is a large language model displays emergent abilities. Now, these are abilities that a large language model wasn't particularly trained for. Rather, when people started evaluating these large language models, they realized that somehow these models were capable of some things, like let's say uh, ability to instruction following or ability to do reasoning, etc. Secondly, large language models provide a new way of using the language model. So we no longer go with the previous paradigm of doing fine tuning. Rather, we use a prompting interface where we prompt the language model to complete a particular task. And lastly, with LLMs, there is no longer a clear distinction between research and engineering. This applies to both building a language model because as the scale of language model increases, you need a lot of engineering efforts to make sure you are collecting data in an efficient manner, processing your data in an efficient manner. When it comes to training the language model, you need to make sure that you're doing a lot of HPC engineering work because you have to make sure that thousands and thousands of GPUs are communicating effectively and the code is efficient. And when it comes to again using the large language models, there is much less of fine tuning, but rather more innovative engineering efforts to make best use of a large language model. Now, this was something about um, the major differences between a pre-trained language model and a large language model. Um, Over the course of this particular session, we'll talk about some background into LLMs. So we'll talk about um, what are the scaling laws, and how did people exactly go from a pre-trained language model to a large language model. Does it follow some trend? uh, we'll talk about, or we'll rather have a brief look at uh, the GPT model's evolution as well as the Llama model. Then we'll go deeper into how to go about building your LLM. So we'll talk about the pre-training data that's available that people use. What is the impact of it? Uh, al- Although the model architecture more or less has remained the same, um, there were some tweaks made so that you could go from 100 million parameters to 1.5 billion parameters. We'll talk about what were those tweaks. We'll talk about what are the different pre-training tasks that are being done, how to do this pre-training efficiently. Lastly, we'll have model alignment and model evaluation. So let's start with scaling laws for large language models. So we know that our uh, large language models, in terms of architecture as well as the pre-training objective, are very similar to your uh, pre-trained language models, such as your BERT and GPT. But what really changed is the model size, uh, the dataset size used for training, and the total amount of compute that has been used for training. So it's useful for us to kind of establish quantitatively what is the relationship among the three. So there have been some studies done on this, and one is called as the KM scaling law, and this from OpenAI. And when they tested, they realized that if you keep increasing the compute, if you keep increasing the dataset size and the model size, in all these three cases, you would notice that your test loss does go down a lot. And uh, you, another finding is that for an optimal um, test loss, you need to be scaling the compute data and the parameter in tandem. So you can't have a large model with less data, or you can't have a small model with a lot of data. This study was done 3 years back. At that point, they only tested from models from 700 million parameters to 1.5 billion parameters. Later, DeepMind came up with their scaling law called Chinchilla Scaling Law. This was around a year back. This time they tested models from much smaller 100 million parameter models all the way up till 500 billion parameter models. And what they noticed is, again, there is a relationship between the compute data as well as the model size, and all three of them need to be in a certain zone for the model to be optimal. For instance, uh, you can't have a small model such as the Z code with a lot of data, which is not optimal, and you can't have a much larger model with less data, because that causes the model to be significantly undertrained. Rather, they arrived at a sweet spot where if the ratio of your tokens to your parameters is 20:1, that gives you a good range for an optimal model. So a question that we have here is that um, among these three things that we discussed, uh, model size, data, and the compute, um, which of these three is the major limitation right now uh, in this year? So think about that a bit. We'll get to the answer in a couple of slides. So we talked about the scaling laws. So it makes sense that, and it has been quantitatively established that it makes sense to improve the scale of the model and keep adding more data to it to get better results. But what people did not realize is that apart from test loss going down, you also notice something interesting that happens in these large language models, and that is your emergent abilities. What we'll do is we'll talk about what are the major emergent abilities that people noticed after they trained the large language models. The first one is in context learning. So when we in context learning, uh, if we provide a context for the language model, which is the demonstration examples. So if we say that for a prompt of review, colon some review, and the sentiment is the appropriate sentiment, and if we give a completely new query within these key examples or this context, the model learns what is the expected output for this. And in this case, we don't even have to change any part of the model. We just give this input directly. This was something new that was discovered when people started training. They did not expect this to happen. Rather, this is something that while doing experimentation that they found out. The second emergent ability is the instruction following capability. So in instruction following, you train a model to follow instructions. So for any task, such as let's say question answering or uh, mathematical reasoning, you give it an instruction like please answer the following question or answer the following question by reasoning step by step. You could also have a prompt such as what is the sentiment of this review and give a review below that, and you train the model to predict the appropriate answer. When you do this, the model learns to generalize to completely unseen task. So let's say if I trained the model on only sentiment classification and I give a new task such as can you predict the can you check if the text is toxic or not, the model will still be able to figure out um, because it's now able to generalize to a lot of unseen tasks. And the third important emergent ability is its ability to do step-by-step reasoning. And this is very interesting because uh, a model, the large language models are actually able to reason out how they are able to arrive at a particular answer. And this is important because reasoning one gives assurance to the user itself that the model did use a particular step of reasoning to arrive at an answer rather than just generating something randomly or let's say hallucinating. And also this reasoning is important because um, we now have a kind of proof that the model did use its world knowledge, or we can check back to see where it's kind of um, getting this answer from. So those were the emergent abilities. We just take a look at uh, what happened between let's say GPT all the way till chat GPT, and we'll actually cover each of these steps over the course of the next session. I mean, course of the session. So GPT-1 was released in 2018, and it was a decoding architecture, and it was trained on a corpus consisting of Wikipedia and book corpus. Eventually, the model was scaled up. It was trained on a bit larger dataset, and GPT-2 was still only around 1.5 billion parameters. Uh, After a year later, this time the amount of data that was used was significantly larger, around 800 billion parameters in 800 GBs in size compared to let's say a few GBs of Wikipedia. At the same time, the model was scaled all the way to 175 billion parameters. This is the first time that people notice that when you increase the scale, you observe in context learning. Eventually, we trained GPT-3 on code to get this codex model. This code part is very important as we'll see later because training on code is what actually gives the model the ability to do the reasoning that we talked about in the previous slide that is over here. Because reasoning out and writing code steps to complete a logic are very similar to each other. And after doing this code pre-training, we have something known as Code Da Vinci, which was further uh, tuned for instructions. That is one of these emergent abilities. It was further tuned using RLHF, which we'll talk about later. And again, it was tuned to follow chat. And over the course of all these steps is where we end up with ChatGPT. And again, we don't know a lot of information about GPT-4, but it also has support for multimodality. Now, is all of this technology and information closed? Not really. There are open source models such as Llama, which people have actually uh, built on top of to get a lot of these techniques that OpenAI did. So Llama could be trained on synthetic data to derive a model like Alpaca, which is capable of doing instruction following. Llama can also be trained on, let's say, chat data, so to make sure that the model is able to uh, follow uh, conversations. Llama could also be connected to multimodal models, such as a vision encoder, to be able to do multimodal tasks like visual question answering or captioning a particular image. So all of this is possible using open source models also. So to probably give a comparison, Llama is somewhere around here because Llama is just tuned for just pre-trained on a lot of different data, including code, and people have been able to do tuning on instruction, doing RLHF, doing chat, and doing multimodal to get their own variants of a large language model which they can use. So this was a bit of background on what's happening in large language models. But now we'll actually go deeper into all the aspects. Are there any questions so far? I'll just stop my screen and check once. So sorry about this constant switching of screens. I have to like stop it to check my WebEx. So we have a question here. Um, how to prepare data for domain-specific fine-tuning of LLM? Example, question answering for agricultural domain. So what we'll do is there's a section here where we talk about um, commonly used corpora, which is coming uh, right now. So uh, I'll answer your question in that part. Another question is which of the open source LLM can be commercialized? Example, Llama. So I can answer this question right now. Right now, there are some very interesting open source large language models. One of them happens to be Falcon, which was the first LLM to be open sourced for commercial use. Falcon is giving quite good performance. Recently have Llama V2, which was from Facebook, and again it's open source right now for commercial use. We have a question. What is the data size for Llama? Again, data size, I'll mention it while we are covering the pre-training corpus part of it. But uh, to give some uh, context, it's trained around 1 trillion tokens. We'll take a look at what all comprises this 1 trillion tokens in the further slides. All right, I'll start share again. Okay, so we'll talk about the commonly used corpus that's being used for LLMs, and they can be broadly categorized into 6 different groups. So we'll start with the first group, that is the books. So this is a corpus consisting of books, and books are a very clean and high quality source of English text. So there's a corpus called book corpus, which was commonly used in models such as GPT and GPT-2. Moreover, there's a corpus called the Project Gutenberg, which consists of all the his books from various different genres. And important thing is they are all in the public domain. So we are free to commercially use this data in our language models. The second source is something known as Common Crawl, and it's one of the largest open source web crawling databases. So it's basically millions of crawlers that have crawled the web, collected any text data that is out there on the internet. So this is a petabyte scale data volume. So it's much larger. However, at the same time, this is very noisy. So it requires a lot of data pre-processing to remove the low quality and noisy data from the web. Another source is Reddit links. So Reddit, for those who are not aware of it, is a social media platform, um, n- uh, very similar to such as Twitter or any other platform. So it's a forum where people can make their posts and others will upvote or downvote them. So upvote is like a like, downvote is like a dislike. And the highly upvoted posts can be considered as useful and can be used to create high quality data. So there's one source is a web text. However, this is closed. It's not released publicly, but people have replicated it to build an open web text. And this is an open source alternative to using social media data. Then we have Wikipedia. Wikipedia is something that has been constantly used since uh, the creation of BERT or GPT. It's a lot of high quality data. Uh, and important thing is it's written in an expository style of writing. That is, it is written with a lot of explanations or with the intent of explaining a particular topic. And secondly, it covers a really wide range of languages. So most of the sources that I mentioned previously were mainly in English, whereas Wikipedia, you do have a lot of different languages. Next is we have code. Again, this is similar to your open um, a common crawl, except that this time we're specifically searching for code, and most of the open source code from GitHub or code from Stack Overflow have been collected. And Google has publicly released a dataset called BigQuery that people are using for their large language models. In others, we can basically categorize other datasets like the pile, which was actually used to train GPT-2 and GPT-3. This is over 800 GB of data, but this consists of multiple sources, including books, websites, codes, even scientific papers and social media platform. For others, you can also use domain-specific data like legal data and finance data, and can be used to train your LLMs. So this is again back to that question one: how much data your Llama model is trained on? So actually, we start from GPT-3. So for GPT-3, with 175 billion parameters, and this was in the year 2021, total of 300 billion tokens were used, and this consisted of mostly from various sources of English text, like Common Crawl, web text, books, etc. The Palm model, released about a year and a half back, that is significantly larger by 40 billion parameters. Uh, that use 780 billion tokens, and this time, interestingly, they have sourced it from again a lot of open source Common Crawl data. At the same time, it does use GitHub. It does use multilingual data. So now there's a shift towards diversifying the data sources, including a lot of different corpus such as code, multilingual data, etc. Now coming to Llama, the sizes vary from as small as 7 billion parameters to as much as 40 billion parameters. This is trained on around a trillion tokens, and this is very extensive. They use Common Crawl. C4 is a very clean version of Common Crawl, uses code from GitHub, uses Wikipedia, uses books, scientific papers from archive, and also a lot of scientific discussions from Stack Exchange. So maybe to answer the question about how to use um, LLMs to do, let's say, question answering in agricultural domain, a good way would be that uh, we wouldn't really require any pre-training as such. What could be done is you can uh, take some question answers from, let's say, an agricultural domain website. Let's say the government of India has a website where they have agriculture related schemes, and they also post some FAQs. You could actually take the large language model and do in-context learning to see if it works. Or you could also do something known as parameter efficient fine-tuning. No, I won't talk a lot about the fine-tuning right now, because that is something that we actually have in tomorrow's session, where we'll show how to tune a large language model. But you wouldn't have to do any sort of domain pre-training. You just need to get, let's say, some 100 200 examples of agricultural question answering, and that should be enough to probably train your large language model. um, so we talked about um, the data that people use, but what are the typical steps in doing data pre-processing for that? So if you have a raw corpus, the raw corpus is not going to be clean, so we need to do some quality filtering. So let's say if you're collecting data for the language Hindi, obviously when we scrape it from the internet, a lot of other language such as English could be part of it. So we might need to use something known as language filtering to remove out languages that we don't want to use. Some metric filtering, so we can use things like perplexity to figure out if that particular piece of code is good quality or not. We could use some statistic based filtering, like if the length is much shorter or much larger. Some keyword based filtering, if you want to remove, let's say, some offensive profanity words. In this stage, you would remove some noisy characters like this. Then you need to do deduplication, because the amount of duplicate data affects the language model a lot. So we can either do it at sentence level or document level or at a set level, such as phrases. Google did a research where they were with what they did is they did a very extensive deduplication at a set level, which actually took a lot of time, but they showed that with a much smaller language model, much smaller data set, which is very deduplicated, they're able to get better results compared to with a non-deduplicated data set. Uh, Privacy reduction. There's a lot of private information in the data that you collect from the web or elsewhere. So we need to identify such things and then replace them with um, some placeholder. And lastly, all of this is still in English or text that we can read. Rather, LLMs require them to be in tokens, uh, that to integer tokens. So we need to train a tokenizer or use an existing one and then encode them into tokens. At this point, they would be ready for training. So what is the effect of pre-training data? So we uh, took a look at what are the data sources being used and what people do to pre-process them. And what we want to evaluate on is how does this mixture of sources help? How does the amount of pre-training data help? And how does this quality of pre-training data affect? So the mixture of sources. So if we pre-train on a mixture of data that includes data from, let's say, social media, from the web, from the books, this diverse source make sure that the model gets a broad knowledge of things. So and it exhibits a strong generalization capability. And this again goes back to that question that was asked about agriculture. So because it's trained on such a mixture of data, we no longer need to particularly adapt it to, let's say, the agriculture domain. Rather, the model will have a good generalization capacity to be able to, let's say, answer agricultural questions, even though it may not have been specifically pre-trained for that use case. Moreover, these specific sources give it some specific abilities. For example, training on books, where you have to keep track of what's happening in chapter 1 to kind of understand what's happening in chapter 10, can improve your uh, LLM's performance on capturing long-term dependencies. At the same time, training on code, because you have to kind of reason out what each and every step in code is doing and what's its purpose, can help the LLM improve its reasoning capacity. Then the amount of pre-training data. So in the scaling law, as well as some other studies, we notice that when we increase the model size, we also have to increase the dataset size in proportion so that you maintain an optimal training state. And to that question I posed earlier, what is the limiting factor right now? Is it data, compute, or the model size? To answer that, um, the model size, people have already made attempts to train a train parameter model, and uh, from an engineering point of view, it is completely feasible to train 100 train parameters, sorry, train parameters, which is like 5 times of what GPT-3 is. And compute, again, it is possible. Compute is becoming much faster and faster these days. The limitation right now is the pre-training data. So internet has existed to the public for the last 20 years, and over the recent few years, we have almost scraped all the data that is actually out there. And going further, uh, there's a serious lack of data, and people actually looking forward to generating their own synthetic data to improve this pre-training. And lastly, the quality of pre-training. I think this is a bit evident. So if you have a low quality text, which is noisy, toxic, has a lot of duplicate data, this will hurt the model performance. So if you train it on toxic data, your model will also be toxic and harmful. Um, so if the model is trained on duplicate noisy data, the pre-training suffers. So when study has been done on training on filtered versus unfiltered, it conclusively shows that the quality of pre-training data is very important. I'll again stop here to see if there are any questions. Right. So one question is multimodal models, multimodal things, can they be handled with Falcon and Llama? So the answer is Llama and Falcon by themselves do not support multimodality. However, people have taken Falcon and connected with it with some vision models such as, let's say, VAT or DETR, and they have made their own versions of multimodal Falcon or multimodal Llama. And we have tested some of them, and they are actually quite good, and they can be used. How to do multimodal and multilingual fine tuning? So the multilingual part is fairly bit easier. In your pre-training data, you just add multilingual data to it. So if you pre-train on, let's say, French, English, and Spanish, you will have a large language model which can do all these three languages. The multimodal part is a bit tricky. Um, at the in a most abstract way, what you could do is just need to somehow combine the input tokens that your model is processing with the outputs or the embeddings that you get from a vision model. So that's a bit out of scope, but I can tell you that there are some papers like Blip or Flamingo, which um, have some very innovative ways of doing this multimodality. Is the pre-processed data available? Um, so one problem is that a lot of this data that let's say Facebook or let's say people who made Falcon use, it's not legally theirs, so they cannot share this pre-processed data. However, um, all the raw data is available online, but we have to do the pre-processing on our own because there are a lot of legal issues with sharing pre-processed data. Um, do we require pre-training or fine-tuning is enough? So let's say you have a llama, llama which is trained on some amount of Chinese data, not a lot, but some amount. You could potentially, and people have done this, you could fine tune it on a lot more Chinese data and get your own Chinese llama, which is possible. So in that case, fine tuning is enough. Again, for multimodality, um, people typically keep their large language model fixed and work with just some fine tuning. some specific layers. Um, does um, does the amount of data from different languages have to be balanced? Yes. So the models, the languages have to be balanced, but that is the interesting part. You don't need to make sure that, let's say if you're training on, let's say, Hindi and Marathi, right? Let's just say that the amount of tokens you have in Hindi is a lot more. You don't need to make sure that you reduce the number of Hindi data. You could simply upsample the amount of Marathi data, and a lot of these uh, uh, frameworks, including Nemo that we'll see tomorrow, have an option where you can specify the weight. So based on that weight, it'll appropriately kind of upsample and downsample data. But yes, they have to be balanced, and that's kind of a important factor. All right. Again, thanks a lot for all these questions. It's very interesting. Um, let's head back to this. So right now we are back. So we finished with our data part of things. So what kind of data we need to use, how we need to pre-process data. Let's move on to the architecture side of things. So we saw in the transform architecture that there were a lot of these subcomponents available. So we had things like um, the embeddings, we had things like the normalization, we had things like the attention, etc. Now, are all of these things the same in GPT-1 and GPT-3? Did people just increase the size of these things, or were there some changes made? So we'll take a look at those things. So we'll start off with the most important thing, that is normalization. So why do we need normalization? When we start training deep neural networks, which are typically more than a few layers deep, it's very important that you normalize the activations that you get. Otherwise, things can get out of hand. The activations can either explode or they can go back to zero. The training will become highly unstable. This was initially noticed in your computer vision. People, when building deep neural networks, such as going from ResNet 18 to ResNet 100, they realized that you need to do some normalization. In computer vision, they came up with batch normalization, which is a really effective technique. Basically, whatever activations you get, you normalize them among the batch dimension, and it works. But the problem with NLP is that the number of tokens that you have, they differ. So in a lot of case, you could have in a batch of, let's say, for examples, you could have sequence of 10, 15, 30, or just two, and a lot of them would be padded up, and this causes a lot of problem. So what people do is they introduce something known as layer norm, and again this was introduced in the attention paper, where you normalize across the feature dimension. So there is essentially no difference between batch normalization and layer normalization, except for um, which axis they are normalizing along. So that is the difference. We have layer norm. Uh, Going forward, there was a new advancement. It's called the RMS norm. So instead of taking the mean and the variance, they just use the root mean square, and that um, slightly improves the speed. And then you have the deep norm. Uh, Again, this was um, kind of a, a advancement from a research point of view, where they try to improve the stability in very deep neural networks. Right now, there's not much difference in terms of what normalization method is being used. Although these two methods show some improvement, people still stick with layer norm, and it works fine for most of the cases. But the normalization process itself is a very important thing in deep neural networks, especially transformers. Now, second consideration when doing normalization is where to place this normalization. Typically in LLMs, you had post normalization where the normalization layer was after you do some computation. Like after you do attention, you have normalization. After you do feed forward, you have some normalization. But the problem was that this became a bit uh, unstable when you kind of try to scale it up. That's because you're already doing a lot of computation and allowing the activations to get larger and larger. And the simplest option was people noticed instead of placing it here, we just bring it back, place it before you start doing activations or before you do any computation. So just this simple switch from post to pre actually improved a lot. And if you start training some language models, you would notice this, that when you're doing post layer normalization, everything works perfectly till let's say 100, 200 million parameters. Beyond that 400 mark, post would really give you unstable training. Your model will start giving you NAND loss, etc. And again, people did experiment with something known as sandwich layer normalization, where you have both post and pre. Um, Again, this worked for some cases, but it's not highly adopted, and people are still sticking with pre-layer normalization. So far we see that normalization, more or less, it remains same, although it's a very important component that was introduced in transformer. And similarly, one other thing that has remained constant is your activation function. Previously, the ReLU activation function was highly adopted in deep learning, but the problem is for all the activations below zero, ReLU just switches it off. So the value for any x below zero becomes zero, which is not a good thing. People kind of came up with something known as exponential linear unit, which is kind of improvement over ReLU. So it doesn't really switch things off, rather makes them negative. Didn't really work well until the introduction of GELU, which is the gated linear unit. And GELU works really well. Uh, it has a lot of properties that make it easy to use it, and it's still being used. There are some variants like Swish GELU and GE GELU. They work in principle in research. They work well. However, practically speaking, they add 50% more parameters. So the performance that you get versus um, the kind of compute you have to sacrifice for it, the trade-off is not worth it. So far, um, in the normalization and your activations, we notice that uh, things more or less remain the same, except for things like maybe the position has been changed. Now, the third thing that we'll talk about are the position embeddings. Now, the attention mechanism, which is like the most important part of the transformer, happens to be permutation invariant. That means the attention mechanism has absolutely no idea about the position of things. So it doesn't know if um, the items are to the left or to the right. It doesn't know how far to the left are things, because it makes sense to us that things which are probably closer to the word should probably have more context versus things that are much farther away. So to fix that, uh, when you provide token embeddings to the transform model, people also add a position embedding. And in the initial transformer models, there were two variants of it. One was called the sinusoidal embedding. So sinusoidal embedding is fixed embedding. So you just have like this sine function which you give to the model in the initial stage. And a sine gives you some amount of information on the distance on where exactly in this function is this item located. So this information was useful, and transformer paper was using sinusoidal embeddings. People eventually started using learned position embeddings. So instead of fixing it to be sinusoidal, uh, similar to token embeddings, you have some position embeddings which are completely random initially. Eventually, the model learns to get some values for them. Both of them used to work well, but the problem that people started noticing is that eventually you wanted to be able to go beyond, let's say, some 512 token positions that you have fixed. So let's say if you in BERT model, it's a fixed position embedding of 512 size. So if you have any document beyond 512, you would have to obviously break the sentence into pieces of 512, which is not very suitable. So people started kind of improving upon this. One option was this relative position embeddings. So unlike your absolute position embeddings, which are added at the beginning in form of token embeddings, what happens in this case is you give this position information directly to the attention mechanism. So for each particular token, you generate uh, two matrices, and these matrices essentially just contain nothing but 0, -1, 1, etc., which indicate the relative distance. So if you're computing for, let's say, the word at, right, you'd probably have a um, value which looks like -1, -2, and +1. That's about it. And you and it's being used in the attention mechanism, and it generated some meaningful results. People did start using this. Then there were some improvements based on this, and this was called the rotary position embeddings. So it uses something similar. This a bit mathematical in detail, but it uses something similar. Instead of directly using some discrete values, it rather uses some um, trigonometric properties of sine and cos. Again, this was useful, was working, but what is actually being used recently, even in the Llama paper, is something known as alibi. Now, if you notice, the alibi is very similar to your relative position embedding, except the fact that uh, with alibi gives some slightly um, better performance because it kind of works on the mechanism of using some penalty scores. So it makes sense again to look at things closer to the word. So it kind of puts a penalty on things which are much farther away, and this seems to work. And alibi is actually being used in a lot of the recent large language models. We won't go much deeper into all these positional embedding mechanisms mathematical part because that'll be a bit too deep. But yes, that was like a brief overview. I'll also check if there are any questions right now. So what is the significant use or importance of layer normalization training process? So what would happen is the training would become highly unstable because uh, with each layer in your deep neural network, what happens is the values are being changed. They're getting bigger and bigger, and eventually things just go out of hand, um, and you would not be able to uh, compute gradients at all because they would kind of just overflow because of how large the values are. And what layer normalization does is it basically normalizes with mean of 0, variance of 1, and it gives you this nice distribution on which each layer can work on. So you could probably try this experiment. So if you just remove the layer normalization from a transformer, even for a much smaller model of, let's say, even uh, 5 or 10 million parameters, you notice that the training process just doesn't work. After a few thousand steps, you would notice that the loss is just NaN. Okay, so I think okay, what is the physical interpretation of normalization? So I'm not sure if I get the question, but if you want to think about this, you could just think that each of these features, they're basically being rescaled. So let's say you do a computation and the values are now, let's say, having a mean of 90 and a variance of no 100. That's pretty large value, and this is just going to get again compounded. The next layer is going to further exaggerate it, and you'll probably get a mean of 100, so on. But it would be nice if all the distributions that each layer sees is just a Gaussian distribution. It just has a zero mean, uh, one variance. So that's kind of one interpretation of it. Any other questions? Okay. So okay, data distribution changes by doing this. Not really. The data distribution overall does not change, but the distribution that each layer sees, that remains same. So that's actually an interesting question, because without normalization, the data distribution that each layer sees at each step or each epoch changes drastically. So let's say one batch had some different data. What layers would see is something very different. For the next batch, again the data distribution would be very different, for that data. However, if you normalize every input that's coming to every layer to 0, 1, the model all the layers in the model know exactly what it is, and they can kind of compare it with what it has learned so far. So it's rather than distribution changing, we are trying to keep the distribution fixed across other layers by doing this. Okay, so I'll start again. So we so far, 1 second. So far we have covered um, the personal embedding part. So now we'll move on to the crux of your attention mechanism. So the interesting part about so self-attention, as I mentioned, is one of the most important parts of the transform architecture, and that is what actually allows transform architecture to scale well. Uh, it's also very efficient implemented, because you can do all of these information, all these operations that I mentioned here, using matrix multiplication, which GPU is very optimized for. And at the core of attention, it's that each and every individual word is trying to look at the other words in the sequence and trying to figure out which word is important for it and which is not. So that was about self-prediction mechanism. And um, if you want to go deep into it, do post the question. But I think a lot of us are kind of familiar with how self-attention works and how attention in general works at an intuitive level. And interesting part about self-attention is, across all these improvements that people have made in architecture, the core attention mechanism itself has not changed. People have proposed a lot of variants of attention, uh, but none of them, all of them, yes, work in certain cases, but none of them are as general as self-attention, and it is still being used in all the LLMs. However, there are some improvements that you can still do in terms of how you implement it. So one such improvement is called the flash attention. Your GPU memory has two types of memory with it. One is called the static random access memory. The other is called the high bandwidth memory. Now, high bandwidth memory, or HBM, is cheap and it's available in a lot of quantity. Your SRAM is much smaller in size, but it's extremely fast. Now, how do we use this information to make our flash attention mechanism better? So what typically happens in deep learning is that all the tensors are stored in HBM, and when you want to perform an operation on them, you do a read operation onto SRAM, do some computation. So in this case, we are doing one computation over here, one computation over here, another computation over here. So imagine this: you do a read, do the computation, write back to HBM, read again, do softmax, write back, read again, do this dot product, write back, tensor again, read write. A lot of IO bottlenecks are present. So what flash attention did at its simplest form is they just wrote a one CUDA kernel which directly takes in the tensor from HBM, and within a single CUDA kernel, it'll do all these multiple processes at the same time or within that single kernel. So now you just have one single read write, and this was the main importance. Apart from this, I think this is kind of mentioned over here, this infographic, where you have all these different operations, whereas in flash attention, you could just do it in a single kernel. Now, this was the most important part of flash attention. Apart from that, it's not exactly trivial to write this kernel. So people had to figure out some mathematical tricks on how to actually make sure you do it. But yeah, those are the trivial details of it. But the interesting part is how much speed up flash attention gives. So compared to just regular attention, the speed up is anywhere from 1.7 times all the way up till 3 times. So some benchmarks show that um, training a GPT-2 model, which have ideally taken 10 days, would just take 5 days on the Hugging Face library and just 3 days on the Megatron LM library. And again, the Megatron LM is the library from Nvidia, which I'll be actually using tomorrow to show the demo. I'll also kind of explain the difference between Nemo, what is Megatron, how it all uh, fixes well together. Okay. So I think so far we just talked about all the architecture changes. So we noticed that in the normalization, the crux of it remains same. The position did change of normalization. We noticed that the position embeddings, people are trying a lot of different position embeddings. So far, Alibi seems to work well. Llama model use Alibi. Then you also looked at uh, your attention mechanisms. Again, it remains more or less the same, except there are some very fast implementations. And flash attention is being used in a lot of these large language models, mostly because it is so efficient in doing the pre-training and also inference. So now we have seen what data people use. We've seen what is the architecture that people have. Now let's take a look at what are the pre-training tasks that people do. This part is simple. There are three different ways of doing the pre-training. One is language modeling, where given a sequence, you have to predict the next token. This is primarily being used in all the language models, starting from GPT. Then you have denoising autoencoding. So autoencoding is the concept where you um, compress data and then retrieve back from the data. And denoising essentially means you have a noise data which you kind of compress and get a denoised output back. So a typical way of noising text is to corrupt it by randomly replacing some tokens, and then you try to recover what is the correct token. You might uh, try to relate this with how BERT model is trained, where random tokens are masked and we are asked to predict that thing. This can also be applied to um, a generative model, and it's how your Day-5 model is being trained. We have lastly a mixture of denoisers. This basically combines these two things together, and it shows that uh, having a combination of both uh, leads to some better language modeling capability. But again, um, although every approach has its merits and demerit, when you're trying to scale a language model, people try to look at what is the simplest option to do the doing the pre-training, which gives you the most bang for bucks. And language modeling seems to work pretty well. And this is still the uh, task that people are typically using. So now we have seen that the pre-training task that people typically use and all the large language models are built on top of is the simple language modeling or the next token prediction. Um, what are the ways you could do this training in a much more scalable fashion? So there are three ways of doing this. Again, I'll just stop, check if there are any questions so far. We'll get back to scalable training. Okay. Uh, we have so please take a break for 5 minutes. Actually, a good point. Maybe we could take a break for we will take a break for 5 minutes at this point. We have some questions here, kind of like effect of convolution for image processing. Um, I'm not sure which part you're referring to for this, like which part you're relating in the slides to convolution, but okay, if you can explain that, it'll be good. Can you provide an example for denoising autoencoding? So a good example would be the BERT model itself. So let's say you have a sequence of text where you have, let's say, uh, again, 10 tokens. Sorry for sticking with this number 10. But yeah, for 10 tokens, what happens in BERT is that you randomly drop out 15% of the tokens. So let's go with 100, right? In 100 tokens, if you randomly mask drop 15 of them into mask, there are like 15 tokens in your sequence which have the value of literally a mask. So it actually says uh, square brackets mask in that position. The task of autoencoding, denoising autoencoding, is to, for each of these mask tokens, predict what is an appropriate word. So that is what denoising autoencoding does. And BERT is probably a simple example for autoencoding. So you're saying convolution for image processing is um, it's kind of similar in the sense that uh, in convolution you kind of also use patch normalization to make sure that each layer has the same data distribution. Mixture of denoisers. So what happens in, so this is a bit deeper into that paper. So there was a paper from Google called UL2. So when you're trying to do denoising, you can either do denoising at a token level. So I will drop out a token called, let's say, uh, good, right? However, I could also do it at a span level where I can say I'll drop a token or a phrase which says good morning. So now you have two tasks. One is denoise a token. You have a task which is denoise a span. You could also make the span much larger. Let's say, good morning, my name is, yeah, basically that's it. Good morning, my name is. You could um, mask it with a token called long span. So we have different ways to corrupt data, and for each of these different corruptions, we have a different denoiser. So that is one way of doing mixture of denoisers. So I think there was a question. I mean, there was a request that we take a break for 5 minutes. I think that makes sense. We have covered uh, quite significant amount of topics here. I'll what I'll do is I'll start a timer for 5 minutes, and we'll come back to this in that.
Yeah, hi, Raman. So it's 7:45. Maybe we can take for 10 minutes and make it 55, and we can start sharp 55 maybe.
Sure. Yeah,
Yeah,
that works.
yeah, sure. Thank you.
So I just started like a timer for 10 minutes. Let's all reconvene back after this. Right, Irwin. I think we just finished our 10 minutes break. So I hope everyone's back. We can get started with continue with our uh, se- the session we are having on large language models. So we do have some questions. Can we use conformer encoder for speaker recognition Nemo? Yes, we absolutely can. In fact, conformer is kind of since it's the SOTA model, we have speech encoding. Uh, we in fact recommend people to use conformer encoder for uh, most of their audio tasks. We can probably also share some uh, examples or notebooks which uh, show this technique. Okay, so I'll just share my screen again. Okay, so far we have established what kind of data people need, uh, what kind of architecture people use for LMs, and we recently looked at what kind of pre-training techniques people do. So now the question comes, how do you ensure that this training it is highly scalable? So there are three techniques which are majorly used. One is 3D parallelism, then you have zero techniques, and then you have mixed position training. And we'll go over them one by one. So first we'll take a look at what are the different techniques in 3D parallelism. So 3D parallelism is one of the most fundamental forms of parallelism, and one of in that itself one of the most important is your data parallelism. Uh, d- at its most basic, in data parallelism, you have multiple different GPUs, and you load model parameters onto each and every one of the GPUs. So imagine you had a small model, right, which is of size 100 million parameters, like the GPT-1 or the BERT model. You can easily fit this model on a single GPU. And if you had 8 GPUs that you have in, let's say, a DGX A100, uh, essentially you can process all of these 8 different models on 8 different GPUs separately. So how it works is, if you have a batch size of, let's say, 64, this is your global batch size. In data parallelism, this batch size 64 is divided into a batch size of 8, and then each of these batch sizes are processed by each separate machine or each separate GPU. Now notice that all of these models have the exact same parameters, and once all these 8 GPUs finish the processing, what happens is the um, gradients from all these different models are taken back into, let's say, your machine 1, that is typically known as your local rank 0. In this, it will be aggregated, and then it will be broadcast again to all these different machines, and then you do a back propagation across all of them. So uh, in each uh, mini batch step, your models have the exact same parameters, but each of these GPUs see a different data batch. So this is very fundamental, and this is at the core of all the different parallelism techniques. Next, we have pipeline parallelism. Now, pipeline parallelism is used when you have a very large model which cannot be fit into a single GPU. So if you have if you have GPT model which has 24 layers, and let's say you can only fit 12 layers in a GPU, you can simply break it up into 0 to 12 layers, and then 13 to 24 layers, and then 0 to 12 layers would be in, let's say, machine 1, and then uh, 13 to 24 are in machine 2. So what happens is you pass your data first through machine 1, get the outputs, pass them to machine 2, and then back propagate again all the way back from machine 2, machine 1, and then do the processing. This is very tricky to implement because typically you don't have two different pipes, you have multiple different pipes. And what happens is, if you have very naive implementation of it, it'll lead to something known as bubble overheads, where one of the pipes at the end just keeps waiting and waiting for one of the pipes initially to finish its computation. So yes, it's tricky to implement. Need to uh, keep uh, track of it. But again, this implementation, we don't do it. It's already done in a library like Nemo or Hugging Face, and we just kind of use it further. Last is tensor parallelism. In tensor parallelism, what happens is, if you have a single layer which cannot even be fit into a single GPU, you can simply slice the tensor in the middle and place half of that on one GPU, half of that on another GPU, and you could just simply do the processes in parallel. The outputs that you get, you can combine them back together and then move on to the next stage. Typically, what happens is that um, all this parallelism is implemented in parallel. So you might have, um, in this case, you have a pipeline parallelism of uh, three. You're using three different pipes. You have a tensor parallelism of two. You're kind of uh, splitting this particular uh, tensor into two different GPUs. And this unit itself, or this model itself with um, pipeline 3 tensor parallel 2, can be distributed across multiple different GPUs to do data parallelism. So typically you use these three techniques in tandem and you get what you call as data parallelism, sorry, 3D parallelism. Next you have something known as the zero technique. Now zero technique is something that comes from Microsoft DeepSuite, and 3D parallelism is something that kind of originated with Nvidia with the Nemo and the Megatron libraries. Zero technique is not a replacement for data parallelism, rather a better way of making sure that your data parallelism efficient. So the big problem with data parallelism is each GPU is kind of processing um, all the data, and GPUs, a lot of GPU memory is being wasted. What zero does is it knows that GPU is very the GPU memory is limited, whereas CPU memory, sorry, as the RAM memory is available to you at all times. And in zero technique, only when a data is being computed by a particular GPU would it retrieve it from the RAM to the GPU. And on the other hand, if the data is not required, it would not be used. So there is some IO over it, but the way it's implemented, it makes sure that overall the process is highly optimized. So it's just a way of making sure that only part of data is actually of used in GPU, whereas most of it is kind of offloaded. So that was a very high level view of what zero does. Obviously, it's a lot more complicated under the hood. But the interesting thing is, uh, 3D parallelism and zero techniques are not to be thought of as separate entities. Rather, um, there is a library called Deep Speed Megatron, which actually combines both of them together to make sure that you're able to train much larger models. So the models like Megatron 530 billion, etc., which have been trained, actually use a combination of 3D parallelism from uh, Megatron, that's it from Nvidia, and then zero techniques from DeepSpeed, that is from Microsoft. Lastly, we have mixed position training. Um, F, FP32 training takes a lot of memory, but the interesting thing with FP16 is you can train a deep learning model using FP16, and although there will be a very slight accuracy loss. Overall, the deep learning model can easily handle uh, doing an FP16 training because it is very robust to changes in data type. And at the same time, given that your deep learning models are robust to data changes in data type, at the same time, your GPUs, they have uh, computing cores specifically built for uh, lower precision computation. For instance, the A100s that we have in the DGX A100s, they have twice the amount of FP16 computation units as compared to FP32. So not only is FP16 uh, faster because it's much smaller in size, it has twice the amount of computation support in a GPU, and hence it's more preferable to do a lower precision or a mixed precision training. Um, FP16 does lead to a loss in accuracy. However, people have come up with a new data type called binary float 16. So this has really sorry about that. So this has much more exponent bits and fewer significant bits. So it kind of uh, trades off between your precision, and this does lead to much better results. So mixed precision training is what's the standard right now in deep learning, and it significantly boosts up the uh, training time. Okay, so at this point, um, to give a quick recap, we have talked about how we can, what is the data we want to use, what is the architecture, what are the training strategies, and how to do this training efficiently. So at the end of this, we should have like a large language model just trained on a diverse corpus, and it's optimally trained. That is, it's not undertrained nor is it overtrained. So at this point, we need to start thinking about the adaptation of large language models. And this goes back to the evolution of GPT that we saw, that after it was trained on a diverse corpus, once it was of a reasonable scale, it was adapted to follow instructions. It was adapted to do using RLHF. So we'll just take a look at these two things. So we'll start off with instruction tuning, and then we'll move on to reinforcement learning using human feedback. So the first step, that is the instruction tuning. Instruction tuning is the task where you fine tune your entire large language model, where you give it a set of tasks, but which are in the form of instruction and an output. So this is an example. So if you have, let's say, a translation task, you would probably give it input instruction like translate this sentence to Spanish, and then you'd give the input itself, and then you would have a target. Now again, you could have something similar for common sense reasoning, like you give a goal, get a cool sleep on a summer day, and how do you accomplish this goal? And you provide some additional information that the task might require, and then you have a target. You do this kind of building uh, prompts, prompt templates for a lot of different tasks like sentiment analysis, core reference resolution, etc. And then you do this training, and what happens is eventually the model uh, learns enough of instruction following that it's not only able to uh, work on these tasks, but it's also able to generalize on an unseen task. This shift is very major because you go from a pre-trained language model, which can all it can do is predict the next word, to be able to actually follow instruction. So you're totally changing the behavior of a language model, and this is like a drastic step in the process of model adaptation. And typically, what happens is when you do this kind of fine tuning, it instruction fine tuning, it really improves your performance on unseen types. So this example given here. So if you have a GPT-3 model, which is 175 billion parameters, and you do either a zero shot setting where you directly give a sample that the model has never seen before. At the same time, you could do a few shot setting where you give a few examples for the model to learn from. Compared to, let's say, FLAN. So FLAN was a paper from Google where they took an extremely large model, 137 billion parameters, and they fine-tuned it for instruction tuning or the task of instruction following. They noticed that for unseen task type, your FLAN model performs much better than even a larger model like GPT-3. So FLAN was kind of the first paper which showed that instruction tuning is scalable and it's um, quite useful. Um, just one point to keep in mind when we're building these uh, training datasets for instruction tuning, you typically have an existing dataset. So this is just an NLI dataset where you have a premise and your hypothesis. And previously, it was a classification task where given premise and hypothesis, you have to predict yes or no. So again, this is a classification task. It was never modeled as a generation task. You could take it and you can build templates on top of it. So you could, and you need to make sure that your templates are a bit diverse so that the model also learns diverse instructions. So you can have multiple templates like these. You can keep some positions where you can insert these values dynamically. So to build this dataset, all you have to do is randomly select a template for each of these samples dataset, randomly select a template, insert the variables at the appropriate location, and that's it. You get a input and a completion pair, and you just need to uh, train it again. Now, one small note is that when you're trying to tune it for the task of instruction tuning, the loss only comes from the target. So, for example, if I have a input of, let's say, translate this task from translate the sentence from English to Hindi, and I have a input which is a long Hindi, long English sentence, and the output is a Hindi sentence. Ideally, in language modeling task, we would compute loss across the instruction, across the English sentence, across the Hindi sentence. All of these are together used to compute the loss. But in this case, I only want to make sure that my target is matching. So the target uh, is what's optimized upon. The loss remains the same. It is the next token prediction loss using uh, your regular cross entropy loss. So what is the effect of instruction tuning? So the effect is one, uh, it improves the performance. It reaches performance as good as your fine tuning and sometimes even exceeds it. You have a task generalization. So if you have trained it on let's say some tasks of question answering, it can generalize to some completely different tasks which it has not seen before. And lastly, it can also specialize in a particular domain. So if you have a language model, let's say in English, let's say like Llama, and you instruction tune it to follow instructions for, let's say, the legal domain or the biomedical domain, you don't need to do any pre-training for legal or biomedical. Rather, you could just do instruction tuning on, let's say, 10, 20 different um, legal datasets. Let's say legal question answering or legal text classification. Um, the model will be able to specialize in that particular domain. So instruction tuning is like a very major step where you go from uh, uh, just an next token prediction model, or as we know as language model, to a model which is capable of following instructions. And if you recall, that is exactly why ChatGPT became popular. We had GPT-3 for a long time, but um, not really one which follows instructions quite well. But with ChatGPT, people are able to give any arbitrary instruction and was able to really give proper answers back for that. So that was about instruction tuning. Next, we actually move on to the alignment part of it, which includes reinforcement learning. Um, I'll just stop and see if you have any questions. Okay, a glimpse of under the hood working of the zero. So this is interesting. It's actually very difficult to explain zero. But there's a very interesting blog from Microsoft where they actually show a video which shows step by step of how this works. I can share that over the chat here. I think that'll be much better than explaining with the diagram. So basically the same diagram I had, but it's actually in form of video. So any other questions? Guys, feel free to post all the questions that you have so far. Um, and okay, get back to let's get back to alignment tuning. Okay, so once we have um, tuned the model to follow instructions, we are almost there to getting usable language model. But there's one small hindrance. We need the language model to align with the expectations from a human user. And typically, the things we're looking for is that we want the language model or the LLM to be um, giving helpful answers. We want it to be honest. We want it to not be toxic. And these information are very difficult to programmatically code it out. On the other hand, we know that deep learning is very good at identifying patterns in data. So the idea here is that if we have humans to actually identify um, which outputs from a language model are useful to them, um, humans will intrinsically choose which output is more helpful given two examples, or which output is um, more harmless. Eventually, we can use any deep learning method to learn these intrinsic patterns in humans' expectation. So, on the high level, that is what the process of alignment tuning is, where we align a large language model with a human user's feedback. And the criteria that we typically have is that one, it should be helpful. So the model should make a clear attempt to assist the user in solving the task and be concise and efficient as possible. Second is honesty. The LLMs should be able to present very accurate content instead of just making stuff up. Lastly, it's very important that the model be harmless. It shouldn't be discriminatory. It should not be offensive. It should be free of stereotypes which are otherwise present in the internet. There are a lot of ways to do this alignment tuning, especially in the last few months. But I think the fundamental one would be the reinforcement learning from human feedback. Uh, this um, graphic gives kind of an overview of how we go from a pre-trained language model to a final end-to-end model which has been aligned with human feedback. So we saw the first step, which is a pre-trained language model, where it's optimized for text completion. So all this model knows is given a text, how to predict the or given a sequence, how to predict the next token in the sequence. That's all it knows about, and this does require a lot of data. As we saw, Llama used a trillion tokens. The next step is the supervised fine tuning, and that was the instruction tuning side of things, where we have a lot of high quality data of instructions, inputs, and the set of output prompts, and we do this fine tuning. And this is again a very drastic step. We go from text completion model to a model which can actually follow instructions. But this last step here, that is aligning with human feedback, is actually um, not very significant. Like the distribution, like the change in output is very minute and might not be even noticeable if we don't evaluate carefully. So the delta here, when you go from this step to this step, is quite small. At this stage, again, you probably require. Um, I think we'll get into the details of how much data is required when we start talking about the uh, RLHF stage. But broadly, this particular stage has two steps. So let's take a zoomed in view of those steps. The first step is to train a model which can follow instructions. This is something that we have already covered. The second step is to train a model that will tell you how aligned is that particular output with human feedback or with humans' preference. This approach is quite common in reinforcement learning, especially with robotics. So, where if you have a robot interacting with an environment, and let's say it decides to do some action, either go forward, go backward, etc., there's always a reward signal that tells it, um, if that particular action was well aligned with the goal. Um, we'll again discuss deeply about how exactly we even collect data for this, how exactly it's trained. But the second step is basically we um, get a reward model where we can give an input, expect an output, and use this reward information further. Lastly, is using a policy. In this case, uh, it's called the proximal perplexity optimization. It's a reinforcement learning algorithm which basically uses the rewards that you get from the reward model and iteratively tunes your large language model so that it becomes more and more aligned with the human feedback. So this was the broadly three steps. Let's take a look at the steps a bit uh, closer in detail. So step two was training the reward model. Now the reward model's task is to take as input a pair of uh, prompt and response, and then it output a scalar value, which indicates if the output is desirable or not desirable for a given prompt. Now we could have annotators whom we could give a prompt and response, and they could sit down and rate it from 1 to 10. But the problem with this is different people will give different ratings for the exact same prompt and response. To make sure that uh, make this thing a bit more consistent, for each annotation that a person does, they are given a prompt and uh, let's say two responses. The goal is for the annotator to select which response is better, which is not. So for a prompt like this, if you're going to steal from a convenience store, do you think it would be better in the morning or night? Now, logically speaking, this response makes sense because this is very helpful. But for a human who is giving feedback, he knows that this feedback, so this output is not the right one. If you want to be honest, if you want to be harmless, you need to be giving this particular response where you just say that, I can't say this. I'm not familiar with stealing items from a convenience store. Typically, what happens, however, is that while annotation, this a single prompt, and there'll be anywhere from 5 to 7 different outputs, and people are asked to rank from 1 to 7. When that happens, um, eventually what people can do to train the reward model is take pairs of two from these. So you could pair up rank 1 and rank 2 to create one sample, rank 1 and 3. Similarly, you could pair up 5 and 7, things like that. Basically, combinations of permutations of two. Once you have this data set, what you need to do next is actually train the reward model. So you randomly sample some prompts, uh, give the output to the language model. This part has already been done, and then people have already scored it and rated it. And for each of these, you train for each of these samples, you train a reward model, which takes in the outputs, takes in the inputs. But again, this time it's a pair of outputs and outputs a scalar value. Um, these are some statistics on um, the data scale and the model scale for uh, training the reward model. So for um, this RHF data, which consists of a prompt, a winning response, and a losing response, you want anywhere from 100,000 to a million examples. The first paper, which explored RHF at a relatively larger scale, was the Instruct GPT, which had around 50,000 prompts. And each prompt had 4 to 9 responses. So, the same way that I mentioned before, you could then take permutations of these 4 and 9 to actually arrive at a much, much larger number of um, samples. The model scale. Now, the reward model um, needs to be at least as powerful as the large language model to be able to even understand what the output is. For example, the OpenAI's 175 billion language model that Instruct GPT was had a reward model of 6 billion parameter in size. Now, this was how OpenAI did it, but almost all the companies that recently have followed up with RLHF actually use the exact same model to uh, train the reward model. So companies like Anthropic and companies like Meta, who recently did RLHF on their Llama model, use the exact same Llama model for their reward models. The model initialization. So we can either train the model from scratch, that is the reward model, or we can start from the pre-trained model, or we can start from the SFT model. It's been empirically noted by OpenAI that if you start from a model which is already done supervised fine tuning, and you take this and you start doing the reward model training, then it's actually uh, shows empirically much better results. So this was the part where at the end of which we'll have a reward model and we can directly use in our algorithm. So I'll just stop here to see if there are any further questions. Right. So one question is, what losses were there in instruction tuning? Was it next sentence prediction, or was it the complete sequence loss? Which one to monitor and when? So in the instruction tuning, we do have the next token prediction loss, but the only difference is this loss will only consider the target part of your tokens, and that's about it. So that's the only difference, because we're not really worried about if you're generating the initial input part of it, because we know that we have given to the model and it most likely will be able to generate it. And how do you handle human bias? So the one way is to actually align it with human feedback. So like we saw right now in this particular example, what we did is we were trying to train a reward model, and the reward model is trained on data itself, where humans have annotated if the data is data is helpful if it's honest, if it's harmless, etc. So the idea is that eventually um, the model will be able to uh, kind of learn these properties of being harmless, etc. But if you're asking, what about the bias that comes from the annotators themselves? Well, that is a tough problem. Um, until unless if you refine the annotation process again and again, that is for each of the uh, rankings, you have multiple, or for each of these samples, you have multiple people annotating it, and then there is a again a pool of people who check if the annotations are in uh, well annotations are in line with the principles. Only then would we can ensure that the annotations are quite good. But again, for the reward model, um, the people who annotate are typically not your normal annotators. They are most likely engineers who have been specifically hired to um, do this reward model annotation, and they again specifically given a lot of training on making sure what a good output and a bad output looks like. But yes, there can always be bias that can creep in. The next question is, how is uh, a reward model looks like? How is it trained? Right. So the reward model is in the case of OpenAI, the reward model for the 175 billion parameter model was a 6 billion GPT-3 model. They again tried this 6 billion with start training a 6 billion model from scratch. They pre-trained the 6 billion and used as a reward model, or they started from a supervised fine-tune checkpoint. So what they noticed is mainly two, maybe the two important conclusions to take from it. Your reward model needs to be at least as good as your large language model. So it should have almost all the knowledge that your large language model has. Now, in the case of OpenAI's experiment with Instruct GPT, that was a very special case because they were only fine tuned, they were only doing the RLHF for summarization task. So maybe they were able to get away with having a model which was at least 20 times smaller than the large language model. However, almost all the other RLHF methods, they use the exact same model that they want to do RLHF on. So if Facebook had Llama V2 to train their reward model, they took the same Llama V2 and then tuned it on the reward model data. What is the hardware requirement for training generative AI? So it depends again on the kind of um, model that we want to use. So typically for let's say a billion parameter model, you can actually easily train it on a single DGX A100 for around 2 or 3 days. But typically for larger use cases, you need to use multiple nodes. Then what is the cost of human feedback, and for how much percentage of data do we take human feedback? Okay, for this, I'll probably share my slides again. And there are some metrics on how much data we actually need. Just give me a minute. So here, in the case of Instruct GPT, they had around 50,000 prompts, and each prompt had around 4 to 9 responses. So you can think of the data requirements in terms of 50,000 prompts. You have to generate for each prompt somewhere between 4 to 9 responses, and um, for each of these responses, you have to each of these prompts you have to do a ranking. So I would assume that this would be a very expensive process. Um, I think OpenAI spent millions of dollars for getting their dataset to do RLHF for doing their RLHF. So that's a very expensive process. To kind of give an estimate, if you didn't want to get 300K, if you just wanted to get some 100K examples, um, the minimum you have to spend would be $10,000, because we were kind of trying to see based on standard rates for MTurk versus the simplest um, setup of feedback data collection. So for 100K data, it would easily take you around 10,000 US dollars. And that too, if you have 10,000 prompts, each prompt has 10 outputs. So that was the, you can use that as a benchmark. And again, for um, training your reward model and collecting human feedback, you typically don't want to go with, let's say, MTurk, because you want to make sure that people who annotate your data are extremely trained. Okay, so I think hope that answers the question. Um, okay, and then the final step is how do we um, finally tune it using the reward model. So for that, we use the proximal pulse optimization. This was a reinforcement learning algorithm that was initially built by um, OpenAI in 2017, and it was primarily used for robotics. You might remember some headlines like OpenAI's model uh, beats the world champion in some chess game, or a lot of these Nintendo games. That was because of this PPO algorithm, and this is only now has it been actually being used in natural language processing. So how does it work? So what happens is you have a huge data set of your prompts, and for each of these prompts, you use your language model to generate an output. Now, in this case, in reinforcement learning terminology, it is called the policy. This output actually goes to a reward model. As you can see, it's again a large language model, and you get an output back. The output is the reward. Now, then you use the PPO algorithm to update this model based on the reward, so that um, with each and every iteration, your model becomes more and more aligned with human preference. Uh, One last step is that tuning using the reward model as well as your PPO algorithm is a bit noisy. So your model can quickly start to deviate and start producing garbage. So to make sure that this doesn't happen, you need to have two things. One is you need to have a loss, which is your reinforcement learning loss. At the same time, you need to make sure that whatever output that the model produces initially from the instruction tune model, which you know is uh, very useful, it may be harmful, maybe uh, maybe not helpful, but you know that this is not garbage. You compute a loss between this model and your RLHF tune model, so that at the very least you're preserving what the model has already learned. So this is a scale divergence loss. You make sure that the distribution of what's being generated same, but at the same time you also make sure that you also use your RLHF your reward model loss also. So again, that's why you give this a slightly smaller rating. So you're trying to balance or do a trade-off between with each iteration aligning more towards human feedback, at the same time um, making sure that your model is not deviating much from your supervised fine-tuning model. And that is why I mentioned that when you go from your initial language model into a instruction following language model. That's a huge gap. That's a huge shift. Whereas when you go from your supervised fine tuning to your reinforcement learning, it's the delta is very small. Uh, Not only because what you're tuning for is uh, very nuanced, also because the tuning process itself makes sure that you don't deviate too much. So this together completes the so this penalization together completes the entire uh, loss that you have in your PPU. So that was about it. So maybe you can do a very quick recap about this reinforcement learning or maybe the entire tuning in general. So you have a large language model that you pre-train on a very huge corpus. Then you have a drastic shift into an instruction tuning model or instruction following model, which takes anywhere from 10K to 100K responses. Then you want to align that with the human feedback. But the problem is that um, for this, it's a multi-step process where you first train a reward model. For that itself, you need to collect some data, train a reward model. Once it's done, you plug your reward model and your supervised fine-tuning model into the PPU algorithm, and you finally get a language model which is aligned well with human feedback. So that was overall of RLHF or an entirety of model adaptation in general. Uh, we'll move into the last section, the final section, which we have, that is the basic ability evaluation. So I'll just stop here, see if there are any questions. Is there a consideration for cultural context in hugging in human feedback? Um, y- so if you mean that we can tune it for a particular culture or something like that, it's certainly possible. But we need to clearly define what is that particular thing we're trying to tune for. But yes, we can actually we just need to define a parameter, make sure that that parameter is actually quite solid, that it's a pattern that the model can pick up on, and we can probably tune it for that. Okay, I think that's the questions we had so far. All right, so finally moving on to the final part of it, that is basic ability evaluation, and that is how do we evaluate a large language model. So LLMs are a bit different in the sense that their capabilities are much more enhanced. So we need to uh, consider a lot of aspects while evaluating. So within this basic ability evaluation, we have three categories. Uh, how well it's able to generate language, how well it is able to utilize its knowledge, and how well it's able to do some very complex reasoning. And within each of these things, we have further subcategories which we'll discuss. So let's start with the most important one, that is the language generation. So for language generation, the first category is language modeling. So it is the most fundamental ability of the LLMs, that is to be able to model language. And the thing we're testing here is, does the model have the basic language understanding? Does it understand English? Does it understand Hindi? And in this case, typically we use metrics like accuracy and perplexity to evaluate the language generation. The second category in language generation is conditional text generation. So this is similar to your language modeling, except in this case, it's conditioned. Uh, can we generate text based on a given condition? So you can think of tasks like translation. You can think of tasks like question answering, etc. And the metrics we use here are metrics such as blue score or rogue, etc. Typically, people also use human ratings to see if the output is exactly what we wanted. And within this language generation, we also have a third category, which is uh, called code synthesis, something that has uh, recently come up due to the ability of language models to generate code. Code is a bit different than language because you need to generate um, tokens or code which can satisfy some specific conditions. And unlike how we were testing language generation or even condition generation, code can be directly inputted into a code compiler or interpreter and be evaluated directly if the output is correct. We can just use the number of test cases passed to figure out how good it's at code synthesis. So broadly, these are three different tasks within language generation that people test their language models at. And what are the issues that we have in language generation? Well, one is uh, the generation evaluation benchmarks that we have and the metrics are intrinsically a bit unreliable. And between human evaluation and using automated methods such as blue score, there's like a huge difference. So if um, we want to translate something from, let's say, English to Hindi, um, the dataset already has a reference translation, and the reference translation means something. We can have a translation generated by the model, which means the exact same thing, uh, but it is possible that um, your automatic reference metrics, such as blue score, they only try to match the tokens. Uh, but for human, both of them make sense. In fact, it's also possible that the output that the large language model generated, even though it doesn't match uh, the wordings in your reference, um, maybe the output is much more meaningful. Maybe it's less formal, something easier for a person to understand. In that case, again, it's um, existing methods are quite unreliable. And the second major issue is it might underperform when you try to do a very specialized generation. So if you are trying to generate for a very particular use case or very uh, specified task, like let's say trying to take llama and trying to um, generate code on it, it might not work as well as you taking a large language model which is specifically trained for code generation. So and that is the reason for things like code generation. We have completely new models such as star coder or CodeGen, etc. Uh, Now we just looked at um, h- what we need to evaluate in language generation and what are the issues. Let's do the same for knowledge utilization. So we know that a large language model, they encode the world knowledge. So when they pre-train on um, large amount of text data, not only do they understand text, but they also understand all the information that you need to know about the world. Like they understand who's the president of USA or what a president even is, right? It understands concepts. So how do we test what knowledge it has and if it's using them? One way is through this thing called closed book question answering, where whatever factual knowledge that the LLM has already acquired, um, the LLM should be able to answer a question only based on that thing without using any external resources. Now, closed book QA, it shows a scaling law. That is, if you increase the model size, if you increase the data size, uh, performance on closed book QA increases. And that's because the larger the model size, the more world knowledge it is actually able to retain encode and during the course of pre-training. Now, this is one way of testing the knowledge it has already acquired. Now, the other option is open book question answering. So unlike your closed book QA, in this case, you can actually provide an external knowledge base or external context to the language model. So it doesn't, so it may learn about, let's say, leaders in history, right? It may know what a leader is, who a leader is, but it may not know who was the leader of, let's say, Morocco in the 10th century, because it's maybe a bit obscure information. But if you provide a Wikipedia document which contains all the information about the leader of Morocco in the 10th century, is the LM able to use the information, generalize well, and give you an answer? That's what's being tested in OpenBook QA. And uh, OpenBook QA is much better because knowledge keeps getting updated and um, updated continuously. And closed book QA is kind of frozen in time. You can't uh, measure its current world awareness based on closed book QA. And moreover, OpenBook QA, uh, a much smaller LLM can outperform 10 times larger LLMs when it shows that when you try to measure its accuracy. So the ideal choice going forward would be to um, have a smaller LLM, which is much easier to train, much easier to deploy, and then connect it to a huge database. It could be a list of Wikipedia documents. It could be even Google itself. And yes, actually, that's something that I think a lot of these companies are doing. I think ChatGPT has plugins where it can browse the web and retrieve latest answers. So yeah, that's similar to that. Lastly, we have knowledge completion. So in knowledge completion tasks, um, LMs can be considered to be part of knowledge base. So a good example is, let's say there's a knowledge base um, or knowledge graph. It's called ConceptNet, and it has common sense concepts such as if there are entities like person, restaurant, and food, the relationship between them in that knowledge graph, which was constructed manually, would contain human uh, is that restaurant uh, will eat food. So there is like common sense knowledge there. LLMs can be asked to do that. It can be given some entities and asked to predict the relationship between them, and we can use that generated links or generated information, try to compare it with existing knowledge graph, and we can kind of get some information on what kind of common sense knowledge your LLMs are encoding. So this is kind of a very uh, high uh, high level task of uh, figuring out knowledge completion. So the problems with knowledge utilization is one, hallucination. Um, in generating your text, um, you're not sure if the model is able to generate the correct answer or not. It might be generating something which is completely out of the blue. Completely, it's imagining something out. And there are actually two types of hallucination. One is intrinsic hallucination, where the generated information is conflicting with the existing source, or it could be extrinsic hallucination, where what's generated can never be verified if it's right or wrong. And for most of the applications, we need to make sure that hallucination is being reduced. A simple trick to actually check for hallucination is if you give the same input and ask the model to generate it three different times. If all three times the model has the same input or same output, most likely it's not a hallucination. But if the model's answers in all the three cases differ a lot, then in that case, it's a case of hallucination. Secondly, a major problem in knowledge utilization is knowledge recency. Since a lot of these language models are kind of frozen in time, so let's suppose we trained a large language model in 2020. The language model might not have any idea about pandemic and its effects. So if you want to train again the model every month or every year, that is an expensive process, and might lead to a loss of generalization, and there are a lot of problems associated with that. So this is again a major issue with how do we encode and utilize the knowledge. The final step is, or the final evaluation kind of category is your complex reasoning. Now, this is specific to LLMs because LLMs are able to work quite well for trivial tasks. So we kind of want to test them for complex tasks a bit. So one is the knowledge reasoning task. So the task here is, if you are given some logical puzzle, are the language models able to actually solve that puzzle or the riddle, and that too using step-by-step reasoning until they reach the final goal. This is an area where large language models are still lagging behind compared to humans, whereas in all other tasks, just question answering, classification, they have surpassed human metrics. The other task is symbolic reasoning. So this is actually a very interesting article that was back in 2017, where uh, Duckling was able to kind of do symbolic reasoning, where it's able to, if it's trained to follow the same colors and the same shapes, it's able to do that. Whereas AI models um, are still struggling with symbolic reasoning. And what happened in 2017 kind of still remains. Uh, Even LLMs have troubles in working with symbols and operations and rules which it has not really seen before in pre-training. And lastly, mathematical reasoning. So this again, puzzles, but mathematical ones, where it has to reason out something from a given passage. It has to use some mathematical concepts. It has to also do some computation, like things like the one we saw in the reasoning example, where given a puzzle on how many apples a person has, it has to reason out, do some addition, subtraction, give an output out. Uh, Now just imagine you make it a bit more extreme. That's what's being tested in mathematical reasoning. So what are the output? What are the problems that we have in this area? Well, in complex reasoning, one major problem is reasoning inconsistency. So an LLM may generate the correct answer, but it may follow an invalid reasoning, or it may produce a wrong answer after a correct reasoning process. Now, this is a bit of problem because if the uh, if this is the case, if there's an inconsistency, then it may be possible that the model is just memorizing the output and somehow filling up some steps in the middle. Uh, Something like we used to do in, I don't know, school and college. Or it is possible that the language model is able to do some steps, but it's not able to connect the dots and it's not able to derive the final answer. So uh, both of them are a problem, and it's a thing that needs to be further researched. And then we have numerical computation. Again, LLMs face a lot of problem when they try to uh, do numerical computation of on numbers or even on symbols. And this is because these kind of problems are seldom encountered during your pre-training. And this is the end of the evaluation part. And there are a lot of benchmarks for each different types of evaluation. And again, new benchmarks are coming up every other week. And I think that was the end of our session on uh, large language models. So to recap, we kind of went and looked at the background for our existing large language models. We realized that what are the key differences between LLM and pre-trained language model. One of them happens to be the emergent abilities. So we looked at some emergent abilities. We looked at the evolution of GPT and what was its analogous development in the Llama side of things. Then we looked at what are changes in data, the model architecture, the pre-training, how to do it efficiently, and adaptation and also evaluation. Um, a very important step here is that uh, how to do fine tuning efficiently. That is something that will be taken up tomorrow. So um, I think that's about it. I'll see if there are any questions right now. Um, Knowledge completion is using LLM is to generate the final answer. Um, so knowledge completion can be formulated in different ways. One way is to um, given a set of notes and links between them, uh, predicting what the output would be, things like that. But the knowledge completion task really varies from uh, one knowledge graph to another. So it depends on the formulation a bit. And uh, thanks for the session. Oh, thanks for all the questions that were asked. It was really very useful. Um, there were some questions regarding T-speed, etc., which I'll probably share the link to in a while. I think Meghna, I think I'm done with the session.
Sure, Raman. Then I think we can wind up in that case. So any more further questions, I'll let you know. And you can let me know the answer, maybe. All right, then. Thank you, Raman.
Thanks, everyone.
Thanks, everyone. Thank you, Raman. And maybe we can continue with the rest of the sessions on Monday, along with the hands-on and the theory sessions, both for ASR and TTS. So for today, maybe we can wind up. And in case you have any further questions, I'll wait for 5 more minutes and please feel free to ping. And thank you all. Thanks for making it so interactive. Also, we're going to have a session tomorrow at the same time. So yeah, please do join using the same link.